Hello, this is Tuğba Ayhan and this video is about DRAM. Here you see the pin assignments for a DRAM. Except from the address inputs and data inputs, we have some important control signals. First, we have the time references for data communication, clock, clock enable, and chip select. And second, we have address multiplexing signals, row address drop, column address drop, and write enable, as well as the address input. These control signals are used to reduce the package size, because both the row address and the column address are transferred via this 15-bit address input, and they are indicated with these two strobes, row address strobe and column address strobe. Here we can see the earliest versions of DRAM cells. In write operation, a word line is enabled and complementary data are written from a pair of bit lines shown on the right and on the left. Charges stored in the parasitic and gate capacitances of the node connected with a high voltage bit line. Since no current path is provided to the storage nodes, storing the charge loss due to leakage, the cell must be refreshed periodically. In read operation, the voltage of a bit line is discharged to the ground through this transistor where the gate node is driven with a high voltage. The read operation is non-destructive since the voltage stored at the node is maintained during the read operation. Here we see another version of DRAM cell. It uses a single transistor, M3, as a storage device, and one transistor to read and write access switch. During write operation, the write word line is enabled and the voltage of the write bit line is passed on to the gate of the storage device through this M1 transistor. During read operation, the voltage of the read bit line is discharged to the ground through M2 and M3 transistors when the gate voltage of the storage device is high. The read operation of the 3-transistor DRAM cell is also non-destructive and relatively fast, but the 4 lines, these word line for read, word line for write, bit line for write, and bit line for read, and their additional contacts tend to increase the cell area. These two types of cells are similar to each other. This is the 2-transistor version of a DRAM cell, and this one is 1-transistor DRAM cell. A separate capacitor must be manufactured for each storage cell instead of relying on gate and diffusion capacitances of the transistors for data storage. The 1-transistor DRAM cell has become the industry standard for dynamic RAM cell in high-density DRAM arrays since the mid-70s. The read and write operations of these two cells are almost the same. For write operation, after the word line is enabled, data are written into the cell through M1, or for this example M2 transistor, and stored at the storage capacitor. Let's look at the operation of 3-transistor DRAM cell. Here you see a DRAM cell with 3 transistors with precharge circuitry and data in circuitry. The storage transistor M2 is turned on or off depending on the charge stored in C1. The pass transistors M1 and M3 act as access switches for data read and write operations. The cell has 2 separate bit lines for data read and data write. So for data write we are using data in, and for data read we are using data out. The operation of the 3-transistor DRAM cell and its peripheral circuitry is based on a 2-phase non-overlapping clock scheme. The precharge events are driven by Phi1, whereas the read and write events are driven by Phi2. Every data read and data write operation is preceded by a precharge cycle, which is initiated with the precharge signal PC going high. During the precharge cycle, we can see the circuitry as shown in this slide. The column pull-up transistors are activated, and the corresponding column capacitances C2 and C3, so they are here in this figure, C2 and C3, are charged up to logic high level. So you can say that they can be charged up to VDD minus VT0 of the pull-up transistor. We will talk about writing a 1 to this DRAM cell, but first we need to see what it means. For the write 1 operation, the inverse data input is at the logic low level because the data to be written onto the DRAM cells is logic 1. Consequently, the data write transistor is turned off and the voltage level on column data in remains high. So this happens when we want to select 1 as the logic data to be written. Then we can go on write operation. The write select signal goes high during the active phase of Phi2. As a result, the write access transistor M1 is conducting. The charge on C2 is now shared with C1 through M1. Since the capacitance C2 is very large compared to C1, the storage node capacitance C1 attains approximately the same logic high level as the column capacitance C2. After write 1 operation is completed, the write access transistor M1 is turned off. With the storage capacitance C1 charged up to a logic high level, transistor M2 is now conducting.